Hello, welcome back to Introduction to Cognitive Science. So far we've been talking quite a lot about how we can represent an information processing system, one that must exist in the real world, as a sort of a physical symbol system in theory. So today we're going to look at how we can actually apply these to things that we could use in either the real world or at least more complex applications that reach toward the real world. So today, like I said, we'll look at some applications and of physical symbol systems that really highlight the use of heuristic search, right? The other half of how a physical symbol system achieves intelligent action. So we'll talk about expert systems, ID3 machine learning, which is related to those same expert systems. We're going to talk about Whisper, which is actually a physics simulation involving a physical symbol system approach, and then Shaky the Robot, a physical instantiation of a logical system that interacts with the real world around it, a bona fide robot. So let's go. Expert systems. So we talked about decision trees in a sense that you may not have, we didn't label them that, but problem spaces, right? So in a given problem, there are many possible routes forward, right? You can make a different choice where you decide to move, how you decide to make a decision. That results in a tree, right? So from each state you're in, you can make a decision and proceed further down the tree. An expert system tries to capture that whole idea and emulate human reasoning using these kinds of decision trees. So, and it has to be very, very well defined spaces, right? So it's not necessarily, a decision tree wouldn't be good for deciding foot placement while you're walking around the world, although arguably you could capture that. But let's look at an example. Mycin. So it is a medical diagnosis tool. And if you're curious, it's named Mycin. It's not actually short for anything. It's just like a common suffix for certain antibiotics and things like that. So Mycin it's a tool, right? It's a medical diagnosis tool. The idea is it's trying to take whatever information we have from the environment. So the patient may exhibit certain symptoms, A, B, and C, but not symptom D, right? So that will define the sort of information space, the problem, and we use that information to navigate the problem space. Also, other more complex information like, oh, they experience A X times per week, frequency information, that kind of stuff. So the idea is that normally if you go to your doctor and you present them with your status like this, they'll work through it and they'll kind of eliminate some things and settle on others, and they will navigate some kind of decision structure to arrive at, hey, it looks like you might have this disease, this illness. And the question is, how do we capture that process for how they arrive there? So Mycin can take all those same kinds of diagnostic bits of information, and then it runs through the search tree, right? So it tries to navigate the problem space of all of, so it's not a problem space in the same sense of, I have decisions to make in tic-tac-toe, but it's still a problem space in that I need to arrive at the correct diagnosis, and there are lots of possible diagnoses to make. So doing that in an intelligent way, using heuristics that we have available, helps us use this to diagnose. So, and it gets to 69% accuracy, which is pretty good because that actually outperforms most human experts. Now, that's not a great replacement for the breadth of human reasoning, right? It can't innovate. It can't pick up additional cues that might not be obvious, right? So the person comes to you and they're pallid and shaking, which are not things they've included on their diagnosis list. It's just a tool. It's a hard instantiated tool, but it's a great automated system that helps first pass, right? You don't need any human whatsoever. You just need to kind of feed in your state to this information base, and it will get you close to your diagnosis, or at least a first opinion. Great stuff. So let's talk about how this works. How do you proceed through a decision tree in this kind of system, in an expert system like this? So from the start state, you will ask questions at each branch. Things like, is A more than X? Is B present? And you will filter down until this expert decision tree helps you figure it out. We will look at an example from lending. Ooh, fun. Yay, money, banks, cool. So what is the applicant's income is the very first question if determining whether or not they are going to, get this loan, right? The bank is trying to help make a good estimate as to whether this is a good idea to give out $70,000 to Joe Schmo, right? So if Joe Schmo doesn't make more than 40K, this is a pretty high-end loan. I don't know that that's a great idea. This is like twice their yearly income. That if the odds are good, things are stacked against them. So you continue down, right? And some of these are a little iffy questions overall, but the idea is that this replicates a similar process to what someone who has been doing this for 10 years or 20 years has arrived at in their own state, right? Now, normal human reasoning, we can kind of jump around these kinds of decision trees. We don't just have to flow forward to a prescribed answer. But these things help to capture, once again, get close, right? So that's the idea of expert systems. They're a way of capturing all this cool heuristic search stuff that we know how to do naturally in our brains, but eliminate the idea of brute force search, right? So just trying a million different combinations of all possible diagnoses, but really trimming the tree down to its bare bones that help make good decisions, intelligent decisions, informed decisions. So what's the problem with this? Well, it's rigid. It doesn't change. It's just, and it has no way to incorporate context. You have to build them by hand, right? So and that has its own issues. I mean, if you just have a person building one of these by hand, they may not know their entire own process, right? They may not know everything that needs to be considered up front. They may be better at doing it than they are at encapsulating it into one of these systems. So we can introduce the concept of machine learning. Now, remember the physical symbol system hypothesis is that all the rules for manipulating symbols are themselves symbols, right? So that means that we can incorporate rules for manipulating rules, right? We can make things that update our own rule sets that help us change them. So if these expert systems can be thought of as in a sense, both themselves as symbols to be examined, but also ways of making decisions like a physical symbol system, then machine learning is a way that we can come in and say, hey, I'm going to just build a method into you that allows you to take new information, a new example of, say, a successful loan or a successful diagnosis or an unsuccessful diagnosis, and allow you to update all of the different branches and numerical values and decision criteria in your decision tree. So the idea for machine learning in a general sense, kind of welcoming you to the concept, is you take a whole bunch of examples, and the examples have to have a particular form, right? The attributes that we're interested in making decisions using, and then some target attribute, like was the loan given or was the loan not given, right? So some kind of success criteria that we can help use to generate, the decision trees. We're trying to arrive at some answer, so we want the answer to be part of these examples. So let's look at that. This tree might be built, so this is the same tree as before. It's not necessarily a pure example of a machine-trained tree, but the idea is you could train this tree up. You could build this decision tree by continuously looking at all the information available here. So we have the income of this example person at the first row, right? They made $45,000 a year. They have 7 years work history, 701 credit score, pretty good. No criminal history. The loan was given, right? So the idea is that you can work in a bit of math here to build this tree. You wouldn't build it after just one, but you start to build these possibilities. So which one of these things determines your outcome the most? Which thing determines it secondarily, third, fourth, fifth, etc. And you can find this way to make the decision tree. So how does this work? How do you actually do this information stuff? So we're going to dig a little into information theory. So where do you begin? And the question is, what is the most informative feature? Which one of these features, the ways that it varies, right, is going to most determine whether or not we end up with the loan or not in this decision tree? This is called information gain. So which feature will minimize entropy, or the concept of uncertainty, right? So we're walking into this situation, and what's the most important thing we want to know about somebody before we offer them a loan as this bank? Going to be their income to start, right? But that's something what we can arrive at in this sort of mathematical way. So let's talk a little bit about entropy, uncertainty, and information. So let's say you have a bowl, and it's full of like ping pong balls. Some of them are black, some of them are white, right? Pick out one ball. If we know all the balls in this bowl, balls and bowls, oh my gosh, spheres in this bowl are white, then we know for sure we're going to get a white ball. We know it's white. There's no uncertainty. Same situation for when we know that the bowl has entirely black balls, right? We know it's black, no uncertainty. If it's half and half, now we finally entered uncertainty. We know it's a 50-50 shot. This is maximum uncertainty, right? There's no way that we can currently make a good decision about this. There's no helpful information available because it's an even split. What if there were 3 white balls and 1 black ball? Well, this is actually pretty useful because now there's still uncertainty. We still can't be sure, but given that we know the base rates of what's going on in this dish, right? We know there's 3 out of 4 are one color, then that's actually a pretty informative piece of information, right? And so it's tough to tie this directly to how the machine algorithm works, but this is the idea. We're trying to find the base rates if the examples are what's in the bowl when we're building the system, then the situations that seem to give us the most informational content, informational value, are the ones that we're going to put first in the decision tree. So, ID3, that's the name of the machine learning algorithm that builds these things. And what it does is it analyzes all of the examples kind of in a very straightforward way. It just says, hey, here's all these examples and how they fit into the outcome variable. Which ones will give us the most certainty? The way they vary gives us the most certainty. So it turns one of these databases of examples into a search tree. So let's look at this example about tennis. Okay, we have a few bits of information here. The day number doesn't really count. Don't care about that one. Okay, what's the outlook? So what do you call that? The weather outlook, right? Sunny, overcast, rain, overcast, sunny, sunny, rain, overcast. Okay, cool. Temperature, hot, mild, and cold. Humidity, high, normal. Wind, weak, strong, strong. Play tennis. No, yes. Right. So each one of these examples was a logged example of, did the people involved play tennis on this given day? So what you can compute is the gain, the information gain of each one of these variables, these columns, right? These features, attributes. So gain is computed kind of in a similar way to like, just like statistical basic probability type stuff. I don't know all the depths of the math here, and I won't push that on you. But the idea is you can figure out, oh, it looks like Outlook is predicting whether or not tennis is played pretty often, right? It's not perfect, but you can see that more often than not, the Outlook will be the most important decision, followed by some of the other ones. So what you can build from here is Outlook is the first question, right? If it's sunny, we got a lot of options. If it's rainy, we've got some other options. It turns out if it's overcast, they always play, which is interesting. Maybe that just makes for the ideal conditions for tennis for this particular group. That's what this particular decision tree would be built with in this scenario. So, and then you can continue on, right? If it's sunny and it's high humidity, no thanks. But if it's sunny and it's normal out, yes, we'll play. Again, all of these things kind of fall out. In fact, you see some of our things, wind and temperature, well, let's see, just temperature. Wind matters when it's rainy, but temperature never really is considered, just because that's how this particular observations database shakes out when you run the system. So that's the idea. You can build these kinds of expert decision trees based exclusively on observed data, and I think it's pretty cool, right? So this is the ID3 algorithm to build decision trees out of raw observed data. So is ID3 a physical symbol system? I think it's fair to incorporate that to make that connection. It's definitely transforming complex symbol structures, right? It takes these databases and turns them into search trees. It uses its own set of rules by, sorting information gain and calculating it and all that. And it creates this new complex structure that can be used as rules for a different decision-making process, right? So the ID3 algorithm itself is helping to create other physical symbol calculations, physical symbol structures, right? So, ID3 and physical symbol systems in general. It's not clear that this is exactly how humans do learning, right? It's not like every time that we go out and play tennis, we are perfectly updating a like perfect database that we have stored in our brains about this. There's likely some other neurological process going on that gets you somewhere close to this, but it does a good job of creating a machine decision-making system, right? So it's this nice movement forward in machine learning that helps us to kind of ramp up the complexity of our decision systems. And it's a symbol system that helps to build other symbol systems, and I just think that's kind of neat. So, beyond just language and symbols and what we've been talking about here, we've been focusing a lot on language, right? The idea that Chinese room is all about moving slips of paper around that have language in them. ID3 is based on feature categories. Language of thought is all about intentional, like internal mentalese sentences, these internal sentences things. And can we do this though? Can we operate a physical symbol system? Can we build a physical symbol system that isn't working with the rules of language? Is language, are we stuck in it, right? So, yeah, symbols don't need to be language. They can be symbols, right? They can be not necessarily generated from a grammar or part of a deep syntax structure. They can just be symbols, arrangements of shapes and patterns, right? what else can we do with that that's not languagey? Enter Whisper. Whisper is a physics simulation. And here's what you input into Whisper. An unstable pile of bricks, I should put that in quotes, bricks, right? Represented by symbolic values in an array, in an input, right? The steps in this process, in this simulation, are a series of unstable piles that are, they will move slightly one step at a time according to a gravity simulation. And then the output will be ultimately a stable pile. So once the bricks have all fallen, once the objects have all fallen. There's no language here. It's just all information is this sort of these abstract diagrams of shapes. Let me show you what I mean. This is a Whisper input. You can tell right off the bat, you can see sort of there's boundaries around each object in this scene. So the 9s at the bottom are the ground. You have on the left, there's a sort of a towering brick with all bound by 1s and filled with A's. There's a triangular brick bound by 2s, filled with B's. There's the sort of the fulcrum over there in the bottom middle, the little spike triangle with bound by 3s and filled with C's, and then this sort of anvil shape bound by 4s and filled with D's. So you can tell right off the bat that this is not stable. This will have to go through some iterations, right? What's going to fall? You can guess to yourself right now. I can just tell you the triangle on the top is certainly going to fall. The anvil might fall. It's tough to say. It could be perfectly balanced. It could be a little off. But the triangle at the top is certainly going to fall. So that's the idea. This is a set of symbols representing some kind of physical scenario. And Whisper will operate on these symbols, move them around in the space until it seems to be stable, right? So Whisper has what you might call a retina. The back of your eyeball is an array of lights, and or not an array of lights, an array of sensors that can detect light, right? We can talk about that another time. But the idea is that Whisper can take all these things like basic concepts of shapes and sizes and centers of mass and all the points of contact. It can detect these things. Those are more of its rules, right? It says, okay, these two symbols are next to each other. That's a point of contact. And that's an abstraction and a new sort of symbolic structure that it can operate on. And it can realize a bunch of things based on its knowledge. So where are the balance points? How balanced are things? Is one side going to tilt or the other side going to tilt after the balance point is detected? So from there, it can run through this very symbolic process of just generating the next state in time. So again, here's the problem. The input. What do you think is going to happen? Right off the bat, you, the viewer, you can imagine, okay, that top one's definitely going to fall. I'm not sure about the bottom right, the anvil object, but block 2 is certainly going to fall. It's going to tilt. It's going to tilt down, and it's going to touch the anvil, which will probably make that not be stable anymore. And then they will both kind of crumble into the valley there. And that is the output. So the idea is that each step, Whisper will say, what is the next possible rearrangement after one little step of time? That triangle is going to have to move a little bit, and then it's going to move a little bit more, until it's in contact with the anvil, and they will both continue, until they are stable again. This is stable because nothing is moving, right? That's actually how you can think about a building demolition. It starts as a stable object, something is knocked loose, and then it ultimately is a stable pile of rocks again by the end, right? So that's Whisper, right? It is a system that tries to simulate a sort of basic version of physics. So when we contrast this with ID3, these are both systems that are using heuristic search, right? They both manipulate symbol structures until a solution is reached, right? So, for instance, ID3 has the simple if-then type of structure that helps you arrive at a solution. Whisper has, it's a lot more possible outcomes, but it knows the rules of physics. It knows which, it knows that the object that has more weight on the left side is not going to tilt to the right. It's going to tilt to the left. And so each one of these little symbols, each one of these little dots on the perceptual backdrop is one piece of the informational puzzle that we have. The perception comes in and we output a transformation that arrives at the final destination. So they're totally different applications. They're very different in the way that they structure the internal problem, but ultimately they're both working well within the confines of a physical symbol system, right? One of these is making complex medical diagnoses and helping decision-making for loaning money, and the other one is simulating physics, but they both are very comfortable in the physical symbol system hypothesis. Okay, so physical symbol systems are a good way to understand intelligent action, right? So ID3's action is to build these decision trees and furthermore help use those decision trees to make decisions, right? Whisper's action is to predict these block instabilities and find the ultimate stable outcome of a pile. But what if we want to ramp things up a bit, make things more comprehensive in real world? Bring in the robot reply. We want our system to interface with reality, not just be a simulation, not just be a decision-making tool. How can we get there? Meet Shaky the robot. Shaky is a robot that takes in the environment around it into a sort of logical form. It uses formal logic to deal with its world. So the world to Shaky is all predicate logic formulas, and the problems that it's trying to solve are these conjectures, and if you recall proofs from back in geometry or any philosophy you've been working on here, the solutions to these conjectures, these problems that it must solve, are proofs. So essentially, its heuristics for navigating the world and for solving ways of interacting with the world are in the form of searching for the appropriate proofs, not just randomly trying things in a brute force way, but finding, known proofs to solve these logical puzzles. And it's named for its jerky movement. So what is it trying to do? Well, I can show you a little video about that.
Shaky was the world's first mobile intelligent robot, embodying numerous breakthroughs in artificial intelligence, robotics, computer vision, navigation, and other research areas. The robot was developed from 1966 to 1972 by SRI International, then called Stanford Research Institute, and its legacy and impact are still very much alive today.
Shaky's really the great-grandfather of things like self-driving cars and even military drones.
The hardware was really pretty primitive, but the software architecture and the software algorithms are what changed the world.
I think we all thought we were doing really interesting stuff, so it didn't really dawn on us that we were doing anything special.
Shaky established a position about what we should be thinking about as possible, as feasible.
To understand why Shaky is so important, we have to go back to 1966, and we have to understand where AI research was at that time.
Well, you have to remember that it was pretty much of a green field when Shaky started. All over the country and even outside of the United States, people were beginning to build the components to artificial intelligence. Nobody had tried at the time that Shaky was launched to integrate all the components of AI and robotics into a single moving vehicle that could reason about the world, could sense the world around it, and could take actions.
Prior to 1966, there were no robots, or at least not intelligent ones. The concept of an intelligent robot was limited to the realm of fiction.
You will meet a charming character in The Robot, always at your service.
When you read the title of the original proposal, it was something like a mobile automaton for reconnaissance. And the reason we called it an automaton was because until Shaky, you couldn't go into a funding agency and say, I want money to make a science fiction kind of device. And so we needed a name. And finally, Charlie, in his inimitable fashion, said, it shakes like hell when it moves. Let's just call it Shaky.
Key components of Shaky's hardware were a TV camera to observe its environment, an antenna radio link, bump detectors, and a push bar to move objects.
My role was mainly get the images and get whatever coordinates they needed to determine where they were and extract the information from the image. I remember when I first saw it, gee, that looks like a dishwasher, on wheels.
While charming, Shaky wasn't impressive for its looks. It was the AI and programming advancements that made it famous.
We structured Shaky software in 4 distinct layers. And that was the first time that a layered architecture was used for robots.
Shaky's pioneering software architecture paved the way to a new era of AI and robotics. The SRI team later developed Flaky, a research robot that demonstrated fuzzy logic and goal-oriented behavior. Then came Centibots, one of the earliest projects in swarm robotics, where 100 autonomous robots demonstrated the ability to map a complex area collaboratively.
I like how it's code that isn't just turning numbers into other numbers. You get to see the thing come to life right next to you.
Shaky also inspired research in natural language-based interactions, leading to the popular speech-based technologies that we use today. Shaky's breakthrough in computer vision is now used to help drivers stay in their lanes. And every time you get driving directions on your phone or a navigation system, you are benefiting from the A-star navigation algorithm, first invented for Shaky. Even NASA's Mars exploration rovers use navigational techniques that were first launched with Shaky.
The future is things like potentially having teams of autonomous aircraft that could go out, for example, and do firefighting, and doing this either fully autonomously or potentially in tandem with human-piloted aircraft that can go out and work with them collaboratively.
Shaky now resides in the Computer History Museum, visible to hundreds of thousands of visitors annually. And in 2017, Shaky was honored with an IEEE Milestone Achievement Award.
The Shaky milestone is important because, first of all, Shaky is the world's first mobile intelligent robot. In addition, this is the first IEEE milestone in the areas of either robotics or artificial intelligence.
Looking back, more than 50 years after the Shaky project began, it's inspiring to see how one small team can make such an impact. How one ambitious idea continues to benefit our lives. How one robot changed the world.
We didn't realize, I think, any of us, what the significance of this was. We knew we were the first, but nobody knew where it was going, and I don't think any of us would have predicted what happened.
Shaky planted the flag way out there. It's a model of the kind of ambitious projects that we should be looking at in the future.
So, I hope this illustrates how this is the kind of technology, this kind of combining all of these parts into this full-fledged robot was kind of set the stage for a lot of advancements. And to recap Shaky's whole situation, right? It has a lot of moving parts that shake around quite a lot. So it has an antenna, so it can link up to other information outside of itself. It has a camera, so it can take in the visual scene around it. It has a rangefinder for distance calculations. It has, and this is the way back, right? So big, beefy onboard logic boards, whereas I'm sure all this would fit in your phone at this point, literally, not joking. So it had a system for controlling the camera, a system for doing the logic, the sort of the predicate solving of the environment. It had a couple of bump detectors, so it could touch and feel, quote. It had some wheels, caster wheel for helping to steer itself or stay stable, but also the drive wheels to move. Okay, lots of parts, right? Shaky is a bit of a Frankenstein, but it's doing a good job. So what's the job that it's doing, right? It is navigating the world around it. So here is an example environment that Shaky might be deployed in. So it's just this little bot, right? And it has concepts about the map that it's on. So as it moves, it kind of tracks its own location, and it can always kind of tell what area it's in. And each of the areas would be labeled with a specific label, right? Like Armis, Rooney, what is this? Dunamis? Right. I don't actually know what any of these stand for, but ostensibly they are unique identifiers that help it track in its sort of logical space where things are located, right? So box 2 is in or is through Demyskull. That's this doorway, right? Door. So, okay, ignoring the complexity of the labels, the idea is that every part of the environment that Shaky is in has sort of a logical representation, a symbolic representation inside of its logic system. So, has a couple of layers of systems. Shaky has a whole bunch of low-level systems, right? So these are the hardware level things, like how do I push my wheels forward to move so far? How do I stop and not topple over? How do I kind of maintain balance? All these little things that take a lot of processing to maintain, but aren't really up in the complex logic area. It's more in the sort of low level, like how do I stop my actuators from making me fall over, right? Versus the higher level systems, which are about the planning, the logic stuff, the course, where do I need to be to solve this puzzle? So that's where all the logic and proofs and stuff live, in this step-by-step solution. So let's run through an example of how Shaky, or in this case, the little person shape, might solve the puzzle. Turn on the light switch. Okay, so it's in this room 1. Room 2 exists but is not relevant to the current situation. Shaky has a few boxes in the room, and there's a light switch on the wall. Now, I'll tell you now, the light switch is too high for Shaky to reach it just by driving over there, turning left, and then touching it, right? It would have to use the boxes. So if its goal is to set the status of switch 1 to on, then its strips solution, this is the name of its logical sort of proof deriving system, it would come up with, after permuting through a lot of proofs and trying to figure out what's the ironclad solution that will get this done, it comes to, well, I need to go to box 1, I need to climb over box 1, I need to climb down off of box 1, okay, and then I need to push box 2 towards switch 1, and then climb onto box 2 and turn on light using switch 1. Okay, so while I've shown you the direct solution to this problem, this is the kind of thing that Shaky would be searching for the plan, right? It would need to go and figure out, okay, like what if switch 1 needs to be on, I need to turn it on, so how would I achieve that? I'm too short. And okay, it doesn't use this kind of language, but these are the kinds of constraints, these logical constraints, that Shaky will navigate to produce a valid solution to do the thing. So that's Shaky. So Shaky shows us a way of taking all of this sort of complex, fully like embodied robot, right? It lives in the world, and thus its interactions have direct meaning. And it navigates the world using this sort of logical process. Now, Shaky also happens to highlight an interesting problem in the realm of robotics, right? So let's talk about that, the frame problem. So Shaky's knowledge of the world, the operations that it has available to it, and its current state, there are a lot of relationships between all of these things, right? There are a lot of, let's say there's 10 boxes, there's distances between all the boxes, right? So the frame problem, distances between the boxes, the relationships between those boxes, the relationship between each box and Shaky, these are all things that would need to be navigated even with a nice, like, trimmed down heuristic tree consisting only of valid logical, proof steps. The issue is that the frame problem is that every time Shaky takes an action, it will change all of the relationships that it needs to sort of process, right? All of the things in the room, all of the possible states update. So Shaky is now farther away from box 2. Box 1 is now closer to switch. Shaky is now closer to switch. This seems very simple in this small world. And that's just the thing. This is why it's a problem. So Shaky is okay with this because Shaky lives in, even though it's technically the real world, I think we can still recognize it as this is still a micro world, right? There's only so many movable objects. There's so many walls and locations and other elements and relationships between the elements in this world. So Shaky's fine with this. There's no explosion possible because all of those processes can be easily, updated, deleted, skipped. Like it can drop out the meaningless ones that it doesn't need very easily. And because all of this stuff can be listed and planned for. But if you scale up a system like this that needs formal logic to navigate, kind of filter across all possible spaces, we get to the issue of the real world, which is that the problem state, all of the possible states that the problem can be in, explodes. And you might not be used to hearing this. Explodes is a legitimate term in terms of this sort of information theory stuff. This is an explosive scaling. They become far too many things to track because every new thing you add has that many more relationships to everything else. So if we have just 10 things, that's a lot of relationships between things, right? That's like at least maybe 100. 10, each one thing connects to the other 10 things, but they also all relate to Shaky, all that. But now what if we have 10,000 things? That's going to be one, it blows up fast. It increases in exponential. So now if you get to the real world where there aren't necessarily discrete states for everything, the frame problem becomes very front and center. How would a system like this handle this explosion? And that it becomes a strong criticism of, hey, wait, Shaky probably is not how natural beings do any of this, although it presents a possible version, right? It is still unto itself an interesting physical symbol system that interacts with the world. So, these are the kind of equal and opposite push of the field of cognitive science. How much is this like humans, and how much is this just interesting on its own right? So, and as we saw, Shaky really brings a lot to the table. It inspires a lot of modern day, very big ideas, right? The Mars rovers operating on similar logic, that kind of stuff. So Shaky does great work. It's not necessarily human, because how would this logical system handle the sort of indeterminacy of being a human being? So that's Shaky. So Shaky being, relating it to the physical symbol system hypothesis, it's just another iteration, right? It has a physical symbol system, And it uses it to solve both low-level hardware questions about how exactly to move and not fall over, and the higher-level, more, quote, cognitive type problems like logic and decision-making, planning, that kind of stuff. So, this concludes our foray into some of the interesting ways the physical symbol system hypothesis is found legs in things beyond just the broad theory, right? Real-ish life problems, right? So expert decision-making for important decisions, sort of these intuitive physics, this sort of best guess at physics, knowing that things will topple in a certain way, and all the planning, problem-solving, navigation type things that Shaky manages to achieve. And again, this is not exactly how humans do it, but it increases the plausibility that something that is a physical symbol system can do things in ways much the same way, or rather, can achieve the same kinds of things that humans are doing. Not necessarily perfectly, and not necessarily the same depth or breadth or generalizability, but they are achieving the same kinds of tasks, and that is unto itself quite interesting. And I hope that this illustrates, too, the usefulness of when talking about cognitive entities that may or may not be human, right? This physical symbol system lens lets us look at them and say, okay, there are some less complex physical symbol systems. Something like Shaky is less complex than a real live human being, but it has its own, it has the rules. It has that basic structure of the field of cognition. So, that's it for today. Final thought. Some might argue that though both are physical symbol systems, Whisper's physics simulations and Shaky's logical planning are fundamentally different. Would you agree? What separates decision-making and planning from physical simulations? Anything? Nothing? More or less than what you might have otherwise thought? All right, that's it. Take care.